Alright, welcome to Lesson 8. We're going to be continuing to find linear factors of polynomials given one factor in any representation. But we're going to continue to look at different scenarios and also to make sense of the situation using the linear factors that we find. Alright, so let's start here. Use the function f to answer the questions. Go ahead and copy down, answer parts A and B on your own. And then we'll go ahead and take a look at that together and see what we've learned from solving this problem. Okay, so is 3 a root of f? Well, what does that mean? If something is a root of a function, that means that it is an x value that makes the whole function 0. So we can test this out by plugging in this x value of 3 and seeing if the function goes to 0. So there I've gone ahead and plugged in 3. You could do this all on your calculator, but I just want to show you what you get. And sure enough, this is equal to 0. If I add the positive values together, I get 38.25. And if I add the negative values together, I get negative 38.25. And those obviously combine to be 0. So this is a root because that particular x value makes the y value 0. So it'll intersect the x-axis. Now, moving on to part B, we want to find all the roots of f and sketch a graph of the function. Well, there's two parts here. So first we need to find the roots of f. And we also want to sketch a graph of the function. Well, these actually have something in common. If we want to sketch a graph of this function, do we want to have it in standard form like this? We can certainly tell the end behavior, but if we want to graph the function, we need to also know the roots. Oh, and that happens to be the other part of the problem I'm trying to find. And both of these are linked because if we have this in this function in factored form, then it's easy for us to find the roots because setting it equal to 0 just boils down to seeing what will make each factor equal to 0. So we want to find all of the factors of this function, all of the linear factors. Well, we happen to know one already, because if this were in factored form, if f of x were in factored form, that means what we're doing is multiplying these factors together, and I'm just going to write two of them for now. If we multiply them all together, then we'll get this function back. And when we multiply them all together, and when we set it equal to 0 to find the roots, it becomes very easy because we're just looking at what will make each factor equal to 0. So we know when we plug in 3 that one of the factors goes to 0, and that factor has got to be x minus 3. So we can use this factor and think about, okay, we want to find something that when we multiply x minus 3 by that something, we'll get our original function back. Well, this leads us to division, right? If we divide our cubic polynomial by x minus 3, we'll find another polynomial that we can use to multiply by x minus 3 to get our function. So we'll use polynomial division to find these missing factors. Alright, so here I've set up my division, and notice that this missing piece here is what I'm going to be looking for, right? When I go through my division algorithm, what I'm asking myself is, what must I multiply x minus 3 by in order to get my original function back? And that's what we're going to be searching for, and that's what we want to find. So if I go through this, and I'll go through the first step slowly and then fast forward. How many times will x go into x cubed? Well, if I want to multiply something by x minus 3 and get x cubed, it needs to be x squared. And if I multiply x squared by x minus 3, this multiplication will give us x cubed minus 3x squared. Now, this is what we get from the first multiplication, but we want to see what's left over. What will we still need to get from the other multiplications? In other words, we'd like to subtract what we have so far from what we want to get so we can see what is left over. So I subtract the whole thing. And when I subtract, I need to distribute in the negative sign. So this becomes negative x cubed, and this becomes positive 3x squared. And as I might have assumed, I don't need any more x cubes. These cancel out. Now I have negative 2x squared plus 3x squared. That's going to be positive 1x squared. And that makes sense because I had a negative 3x squareds and I needed negative 2x squareds. So from my next multiplication, I get a positive x squared, I'll be in good shape. And then, of course, I still need all of this. Negative 6.75x plus 11.25. All right, so at this point, I'm going to skip ahead to the final answer so that we can make sense of it. So here we're all done. We've finished the division, and luckily we've gotten a remainder of 0, which tells me that when I multiply x minus 3 times x squared plus x minus 3.75 together, I'm going to get exactly this polynomial that I had originally, and there will be nothing left over that I'll be missing. So I can go ahead and now complete the other portion of my factorization. I know that when I multiply x minus 3 by this quadratic, I'm going to end up with the original equation. So I can rewrite f of x as exactly that, x minus 3 times x squared plus x minus 3.75. So what you notice is that we've factored our function. We have one linear factor, x to the first power minus 3, and then we also have a quadratic factor, x squared. What makes linear factors so helpful is that if we're trying to find the roots, in other words, if we set our function equal to 0 to try and find the roots, it's very easy to use a linear factor because when you multiply two things together and they equal 0, one of them has to be equal to 0, which means that for this particular factor, x would have to be equal to 3. And so, well, what about this other factor here? This is a quadratic, x squared. One of the things we've tried previously is actually factoring this quadratic into two linear factors. And that way we can use those two linear factors in the same way we looked at x minus 3. But you probably notice it's not so easy to factor this in our head. So what we need to do is utilize some skills that we have previously. Remember, we're just asking ourselves, what will make each of these factors equal to 0? So the first thing that we did, our first option, was to set x minus 3 equal to 0. And that, of course, told us that x must equal 3 in order to make that happen. And that is one of our roots. Well, we can take this exact same idea and apply it to the quadratic. Remember, we are multiplying two things together and they equal 0. So either this equals 0 or this equals 0. In other words, we can set x squared plus x minus 3.75 equal to 0. And if we solve for x, we'll find the x values that will make that equation equal to 0. Make this function equal to 0. Well, how do we do this? We could use the quadratic formula to solve for x. This is a quadratic function that we're setting equal to 0. So remember quickly that when we're solving a quadratic, we always will get two solutions. They could be a real solution that's repeated. It could be two distinct real numbers, or we could get two complex numbers. So keeping that in mind, you can use the quadratic formula to solve for x. So go ahead and do that now. It's good practice, and I'll put the answers up so that you can check your work. Using the quadratic formula, we get two more roots. They're different. Negative 5 halves, or negative 2.5, and negative 3 halves, which is 1.5. So now with these three roots, we can go ahead and actually sketch a graph of the function. Before we do that, I want to point out how we can also use each of these roots to write the function in fully factored form. Because now that you know all the roots, you can actually write all of the linear factors. So my function, f of x, is x minus 3 times x plus 5 halves times x minus 3 halves. That's my fully factored form, and now I can use this to go ahead and sketch a graph of the function. making a sign chart to find out what's in between each of the roots using the end behavior of a cubic with a positive leading coefficient. And I could also use the shortcut of noticing that each of these factors is multiplicity 1, which means they're going to cross over the x-axis at the roots given by each of these linear factors. So go ahead and sketch a graph on your own. I'll put up the finished product of what the graph should look like in a few seconds, and then we'll move on to practice with some more problems. All right, let's go ahead and take a look at the graph. As you can see, the end behaviors, the right end behavior is increasing, the left end behavior is decreasing. I have the roots negative 2.5, positive 1.5, and positive 3. And the function is crossing over the x-axis, going from negative to positive, and then positive to negative, and negative to positive at each of the roots. And I could use my sign chart to figure that out if I needed to by plugging in a value in between negative 2.5 and 1.5, perhaps 0, and seeing that it will be positive when I plug in 0. I could plug in a value between 1.5 and 3, or perhaps 2, and see that it will be negative there, and that could help me figure out what happens in between as well. All right, so here are 3 for you to go through. Make sure you take your time with these. They're not supposed to necessarily go quickly, but what you want to do is make sure that you're coming up with a plan for each part. What are you going to do? What is what you do help you towards finding what it is that you're trying to find? And really put some thought into each of these so that when you show up on Monday, you'll be more prepared to tackle kind of the next set of challenges.